So in this lecture we gave a first introduction to norm and trace, and we will revisit these definitions again and define them separately later on. So norm and trace we want to talk about. So first start with some matrix. So say we have a n by n matrix, say call it A, we write it as Aij. So we can talk about trace of this matrix and determinant of this matrix. So trace of the matrix is just some of the diagonal entries of the matrix, and determinant, the standard determinant, and this is how the standard determinant is written. You basically expand out all the terms, and the sigma is the permutation. This second symbol is being permuted, and here you write the sign. So this is the long form of writing the determinant, but this is the standard determinant which we have learnt in linear algebra. So now we talk about the characteristic polynomial associated with this matrix A. So the characteristic polynomial, you have this chi ax. This is determinant of x times, this is identity matrix which has the size n by n minus a. So this is the characteristic polynomial. So now we come to the definition of norm and trace. So you consider this field extension L over K, and this has degree n. So then L is a finite dimensional vector space over K, and this dimension is precisely n. So now you pick up some element y in L. So you're picking up element y which lies in L, and then we can talk about multiplication by y. So we just have a map from L to L, and you take an element here, you multiply it with y, and you end up here. So say you take an element here k, multiply with y, you end up here ky. Now but these are vector spaces. So this is a finite dimensional vector space. So therefore multiplication by y essentially would mean that we have to associate to it some k linear transformation my. So this is a matrix which is associated with multiplication with this element y. So these two are related. So now we are going to set this matrix again, it has elements aij to ay, and we are putting in y here to signify that these elements are coming from here, the multiplication by y. So this is our new matrix which corresponds to simple multiplication by an element y which lies in L. So then you can talk about trace, which is trace of this associated matrix. You can talk about norm, which is determinant of this matrix, and you can talk about characteristic polynomial associated with this element y, which is again a determinant exactly like here. So again, this dimension of this I identity matrix depends upon this degree of extension. So here we are saying degree of extension is n, so this is n by n identity matrix. So let us do some examples and calculate trace, norm, and characteristic polynomial. So first consider this extension. This I is a complex number which is square root of minus 1. So now say y is a plus bi, and this y we are taking in this qi, and the basis of this vector space qi over q is just 1i. Now if you want to study multiplication by y, so this here a and b are both rational numbers, so if we have to study multiplication by y, that is just this element, we have to study its action on the basis elements. So basis is just 1 and I, so you multiply a plus bi with 1, you will just get like this. This is 1 here, I here, the basis elements, and then a plus bi times I. So then you get minus b times basis element 1 here and basis element I here. So from these two things we can get the multiplication matrix. So this a and b form the first column right here. So these two would come right here in the first column, and these two would come right here in the second column. So this comes to the second column and this comes to the first column. So now you can compute the determinant and add the diagonal elements. So you add the diagonal elements, a plus a, you get trace as 2a. You compute the determinant, you get a square plus b square, and that is the norm of this y. Then you can also compute the characteristic polynomial, which will become, so we have to multiply x by 2 by 2 matrix. So you will have some matrix like this, x0 0x, from which you will subtract this matrix, and that will give us something like this, x minus a, x minus a. So this minus b with this negative sign will become plus b, and this b will become negative b. So now you have this thing, and you compute the determinant of this, which will be x minus a square plus b square, and that's precisely what we have right here. So we have computed the characteristic polynomial, norm and trace. Now let us try changing the basis elements and see what is the impact on norm, trace and the characteristic polynomial. So now we are going to change the basis. So we are keeping this element the same as this element right here, but the basis is now changed to 1 plus I and 2i. So again, to study multiplication by y, we study its action on the basis elements. So a plus bi times 1 plus I. So you can expand this out, it will give you a minus bi, a plus b, but you have to write this in the term of basis elements. So you reformulate this as 1 plus I and b times 2i. Again, you have to study the action of this on the basis element. So you multiply it with 2i, which is the basis here. Just like the basis here was 1 and I, here it is 1 plus I and 2i. Expands like this, but you have to write this in terms of basis elements. So you have minus 2b 1 plus I and a plus b 2i. Now copy these two terms in the first column here, and copy these two terms in the second column here. So now you compute norm and trace. Again, the trace is given as 2a and the norm is given as a square plus b square. So you can easily see the determinant is a square minus b square plus 2b square. Now we talk about the characteristic polynomial. So again, you have x0 0x, from which you will subtract this thing. You get plus 2b here and you get minus b here. You expand it, you get x square minus 2ax plus a square plus b square. So notice that the characteristic polynomial here and here are the same. So are the norm and trace. So this and this are the same, and this and this are the same. So this is not a coincidence. This is precisely because if we change the basis, the matrices we get, this matrix and this matrix, they are both conjugate to each other. So these two matrices are conjugate. So the result which we have is that this is this norm, trace and characteristic polynomial are independent of the basis. So let us recall this result more formally. So if we change basis, we produce a new matrix which is actually a conjugate of the previous matrix. So two matrices M1 and M2 are called conjugate if there exists an invertible matrix U such that M1 you can write as U, M2, U inverse. Now conjugate matrices have same trace and determinant. So this can be seen in a course on linear algebra, and this is how the characteristic polynomial is written like if you actually start expanding it. So if you expand it, this is what it will come out like. So here is the trace terms, that is, this will be the sum of the entries in the diagonal, and this last term without any x would be determinant of a. So this is just comes from the expansion of the determinant associated with the characteristic polynomial. So recall determinant of, we are saying xi minus a. So if you compute the determinant this completely, you end up getting determinant of a here and trace of a here. And again, this above does not change if we replace a with ua u inverse. So again, a fact from linear algebra. So therefore you see that trace, determinant and the characteristic polynomial, they are independent of the basis. So every time you change basis, you just are getting another conjugate matrix which will have the same trace, determinant and the characteristic polynomial. So now what have we done? So for any two endomorphisms alpha and beta of vector space, so say alpha and beta, you can say L over K is a vector space. You can consider this alpha and beta as elements of L. So this endomorphism alpha and beta is just multiplication by L. So you're going from L to L, you're multiplying by alpha or you're multiplying by beta. And you can talk about trace of alpha plus beta, which is just sum of trace. So trace is additive. As you can see, just taking two matrices, whether you sum up the diagonal entries before you add the two matrices or after you add the two matrices, it is going to remain the same. So trace is additive. And since you have this property of the determinants, determinant of alpha beta is determinant of alpha times determinant of beta, you can see norm is multiplicative. So notice that we have an injective map. Say if you just consider this alpha as multiplication, to alpha you are adjoining a matrix which we are writing as M alpha. So we were writing y, and to it we adjoined a matrix My. And notice we are saying this map is injective. So there is a homomorphism from L. So just from multiplication, taking an element of L, multiplying it by something and ending up in L. So there is a homomorphism from L into the ring of endomorphisms of L. So that is the matrices which take vector space L to L as a vector space over K. So that we already knew. So to every element Y we are attaching a matrix, and this matrix we are calling is the ring of endomorphisms, because you can add these matrices and multiply like this. So for alpha not equal to beta, we will get that these two matrices are not equal to each other. That is precisely the proof of this map being injective. And this follows because we can always recover alpha and beta from these matrices. We just evaluate these matrices at 1 here. M alpha you evaluate at 1, you get alpha, and M beta you evaluate at 1, you get beta. We are saying alpha not equal to beta here, so we get this here. So a few more examples. So now consider this extension L over K. So K is rationals and L is you have adjoined 2 1/3 to rationals. And now our y is a plus b times 2 1/3 plus c times 2 to the 2/3, where a, b, c are rational numbers. You take the spaces 1, 2 1/3 and 2 to the 2/3. Now to study multiplication by y, we study its action on the basis elements. So you take this entire y and you multiply it with the first basis element 1. Then you take this entire y, multiply with the second basis element, take this entire y and multiply it with the third basis element. So once you multiply here, nothing changes. Here you're multiplying by 2 1/3, so a times 2 1/3 comes here. You multiply here, you will get just 2c, and then because you will get 3 by 3 here, then you b, this will give you 2 2/3 here. Again you multiply here, a will come here, then you multiply this with the b, you will get 2b right here. You multiply with this with c, you get 2c 2 1/3. So now you put this into matrix form. So this first row becomes first column right here, a b c. The second, this here 2c a b becomes 2c a b, and this 2b 2c a becomes 2b 2c a. Now again you compute norm and trace, compute the determinant, write it as a norm right here, and you can see the trace is 3a. You write it here. So the sum of the diagonal entries. Now another example. Now you adjoin alpha to rationals over rationals. So L is this, K is this, but alpha is now root of this polynomial here. So if you plug in alpha here, you have alpha cube minus alpha minus 1 will become 0. So that is alpha cube will become equal to 1 plus alpha, and this is we are going to use. Now you take some element y with a plus b alpha plus c alpha square, where a, b, c are rationals, and the basis of this vector space you take as 1 alpha alpha square, because this polynomial has degree 3 here. This is a reducible polynomial. So to study multiplication by y, we study its action on the basis element. Again you take this y, you multiply it with the first basis element 1, you take y, multiply with the second basis element, take y and multiply with the third basis element. You multiply with 1, everything remains the same. You multiply here, you get alpha cube. This alpha cube you replace with 1 plus alpha. So you get C plus A plus C alpha plus B alpha square. Similarly here, every time you get alpha cube, you replace it. So we will get something like this. So this C alpha 4 you will replace with alpha times alpha cube. So you will replace it with alpha plus alpha square. So you will have C alpha and C alpha square. So this is C alpha square and this is C alpha. And then you expand it out like this. So you get the corresponding matrix. This A, B, C come right here, A, B, C. Now you have A, this C right here, A plus C and B, and then you have B, B plus C and A plus C. So again notice we are using the basis elements. So 1 alpha alpha square, again you have the basis element here, 1 alpha alpha square, basis element here, A times 1. So you have to use the basis elements to convert here. So this becomes this column right here, and this became this column right here, and this became this column right here. So now again compute the norm, compute the determinant of this. You get the norm, add the diagonal elements, this, this and this, you get 3a plus 2c, and that is the trace. So now again we consider this extension L over k of degree n, but now you take this element a from k, from this underlying space. So now to study multiplication by a, we study its action on the basis elements. So what we get is you just multiply a with the identity matrix because it is coming from k. So it is k linear transformation. So this is all it will come out to be. So if you just take an element a lying in k and you talk about multiplication with a, you're going to talk about such a matrix. So again you can talk about the norm and trace. So sum up the entries on the diagonal, you get n times a, because this is an n by n matrix. This is in here, this n is precisely coming from this degree n here, and a norm is just the product of entries on the diagonal, so it is a to the n.